Howdy, everybody. Hope you're doing well wherever, whenever you are. All right, I just had to go look, make sure things got started. We're here for Quest 16 of Everybody Codes 2025, song Ducks and Dragons. Been pretty good so far, but I just realized like we're coming to an end, right? So, uh, I did get a chance to do this one last night. I did do it a little bit late, and so I didn't have time to record. So I'm recording in the morning. I'll publish it in the morning. Um, but I'll be excited to see that maybe that's giving you time to solve it. So hopefully I'll have more time. I'll be able to see more solutions on Reddit, and I'll particularly look for commenters and people that I've seen before. So, um, uh, the way the story kind of continues is, you finally make it out of the cave, and now you find your way to like some guardians, an order of like people who have meant to like maintain and watch over the dragon ducks and especially the golden ducks, which it seems more and more likely we are. And they have a spell that you cast to build a wall, and that's kind of what it is like you're going to be building this wall or figuring out how many bricks are required in the wall or how long you can make the wall given the number of bricks and stuff like that. That's kind of what the day looks like. It's very math heavy, at least in my mind. I mean, it's not the heaviest math problem, but it's more math related than I think it is like algorithm related. But the math part of it, I think, is necessary to make it even solvable. Like in the third part, I tried to do it like without math, at least for part of it, and it just was not working. And I guess in that case, I actually did use an algorithm. So we'll talk a little bit about binary search today. Reminds me, I need to pull out my pen and such. Because yeah, we want to talk about. I don't think I've ever shown a binary search because most of the time you can actually just do a binary search. Most programming languages have it in their standard library, but we'll talk about it a little bit briefly so you can kind of see how it works and hopefully it makes sense to you. Okay, with that, let's just move on to part one. So again, they're saying, hey, we have this pattern charm spell, and it tells you when to place bricks along the wall, right? And the way that they describe it is if you give them a 1, you place it at every column. If you give it if you're given a 2, you place it every other column. If you give it a 3, it's every third column, and so on and so forth. So you can think about this. We've done problems like this before where it's like I think we've done an advent of code where it was like elves delivering to, every other or every third and so on and so forth. And so what they say is they're going to give you an example input right here, right? So 1, 2, 3, 5, 9. And what that means is you have to like kind of build out the wall from those things. And so like they for part 1, they just want you to do it 90. What does it look like if you've done 90? So you can see here that I think this one, it actually gave you some really good examples to like highlight it. So since you have the number 1, you want to place 1 in every single of the 90 columns, right? And then the number 2 is every other column, right? So now it's going to fill up those. 3 is every third column, right? So you see it's like placing it every 3, and this is like building up a wall. Then every 5 is like, now it's every 5 columns, right? And so you're going to build those up. And then every 9, now you're counting every 9 and placing it every 9 times, right? And so like what it's saying is once you've done that, if you sum up all of the bricks that were used or all the blocks that were used, for this example, you get 193, right? So you're basically like laying bricks based on the numbers you're given, and then you sum up all the bricks you used. I think this one you could definitely, like, if you've never done a problem like this before, this first part, you could definitely say, oh, I'm just going to create an array of 90 and then I'm going to count and add values as I go through. That would totally work, just because the numbers are small. The approach that I took is actually, you'll see it's quite short. I just do this right here. So the idea, obviously we need to parse the input, and it's just commas and integers. So that one, nothing really super interesting about that. I just split and do parse. I am doing unwrap. If you've been following the unwrap gate stuff, yeah, I think we've mentioned it multiple times. You shouldn't be unwrapping in real code. This puzzle code, so it's fine. I have a couple, like I've been working on some of the other Everybody Code stories, and one of them I had just read the unwrap article, and I'm like, oh, can I do the whole thing without unwrap? It adds a lot of code, right? Because you have to do error handling all over the place. And I will say, just as an aside, I actually don't mind languages like Go and Rust where they're like explicit, and they're like, if you want to do error handling, you know, we're going to provide you errors that you can then manage, right? Rust is different. Well, I guess Go is the same way too. You can totally ignore the errors, right? You can just say I don't care about the errors. But it's going to give you errors, and you have to handle it. In other languages, they can be kind of obfuscated, right? Like C, for example, you may get an opcode, or you may have to look for like an error code somewhere else, right? And so it may not even be obvious to you that an error has occurred, and so you have to be much more mindful of that. There's other languages too where you're like wrapping it in try blocks, and that can make it hard. I do like the idea of being explicit when you want to, but when you're solving puzzles. So, okay, back to part one. Well, what are we doing is we're laying bricks, right? And we're doing it from 1 to 90 columns. And another way of thinking about, if you look at each column, if you ask yourself, would I place a brick there? You're just asking yourself, for each of the inputs, is it a multiple, right? Does it divide evenly by that thing? So like the third position would have 1 and 3. The fourth position would have 1, 2, and 4, right? And so you just ask yourself, for all of the inputs, filter by the ones where it is a multiple and count those up. And you're going to do that for every column, and so you just sum them. This one actually turned out to be very functional, I think. Nature. I did a lot of functional style stuff. I guess not the bsearch, but anyway, that was it for part one. For me, it wasn't that hard. I just said, oh, I can just go through the 90 values, or the 90 columns, and for each input, see if it's a multiple of it, count it, and then sum it. And this, I mean, you can see it returns really fast, right? Again, the input's relatively small, so these solutions, they solve pretty fast. And again, it's also very math heavy. So like I suspect you either solve in microseconds or in days, like that. Like those are the two polar opposites of solving these problems. Okay, so what happens in part two? Well, now they say, well, what if we do the reverse? What if we give you a list of columns and their sizes, how many blocks or bricks are in each column, and then can you figure out what numbers should be represented by this? And I kind of want to describe this to you a little bit. I think the way to think about this is, sorry, I didn't set any of this up. The way to think about this is like, you're going to have an array, right? You're going to have this like big array of numbers, 1, 2, 2. What were they? Oh, it's right here. 1, 2, 2, 2. Is that it? Did I miss one? 4 2s and a 3. So this one's it took me a little bit of thinking, but I think I got there relatively fast. Like the thing that I was trying to go through my mind is like, at any point in time, how do I determine like what numbers contribute to this one? And like my thinking is like, so like if I'm over here, how do I know which three numbers, right? There's some set of numbers, 1, 2, 3, 5, 7, and 9, right? That, like if this is the spell, which of these numbers contributed to placing this 3? Okay. And the way that I want to do this is I want to label them with their index, because that's what you actually use. So like here's the index and here's the number, and then here is your spell, right? So presumably you have the spell. You don't know what this is at the time, but you go 1, 2, 3, 4, 5, 6, and so on and so forth, right? So the thing that went through my mind is, okay, well, 1's pretty obvious, right? If there's a value here, then it must be a 1. There's no other value that it could possibly be, right? So you know that this one, in order to get this one, it has to have a 1 in it, right? The spell does. 2 is a little bit the same, right? It's either a 1 or a 2. So if it has the number 2, we know that it must contain all of these, right? In the same case in this one. If this 3 is a 2, how, what could contribute to that? Well, either a 1 or a 3, right? And I'm illustrating this because if you think about what you're actually doing is you're saying, well, what are the factors of this number? Right? What are the possible like numbers that you can use where their product is equal to that number? And so for 1, it's just 1. For 2, it's 1 and 2. For 3, it's 1 and 3. For 4, we can use 1, 2, or 4, right? You can use those 3 values for 4. And so that's kind of what was going through my mind, is like, oh, if I get the factors, I could potentially figure out which ones are in there, which ones would be used, right? So the algorithm is such: get the factors of the number, and then see how many of the factors are in the spell. So the steps are factors, 2, so F in spells, and then 3, if less than n, add I didn't do that very well. This is like the general algorithm: get the factors, see how many factors are in your spell list already, and if there's any, if they're not the same, then you now know you're missing a number, and so it must be the ith number, because presumably as you've gone through this list, you've found all the previous ones, and so there'd be no one less than it, only one equal to it. So you can do this with this, right? The factor of 1 is 1, and you initially start with an empty set, so you know you can add 1, right? So now when you're here at 2, the factors of 1 and 2 are 1 and 2. We only have 1 in the spell, so we have 1 missing, so it must be this ith value, which is 2. So now we do 1, 2, right? 3 is the same, right? We say, oh, there's 1 factor here, or there's 1 factor that we can potentially use from 1 and 3, and so we're still missing 1, so 3 must be in the list, right? So now we have 1, 2, and 3 in our list, right? 4, we now say 1 and 2 are a factor of it, so we have 2 of them, but we were looking for 2, so that actually doesn't add any. And you just keep going on and on like this, right? For 5, eventually you go through the list, and now you know, oh, I've completed all of the values. I've solved all of them. And that's how you solve it, right? At least that's the way I solved it. Potentially there's another way, right? But the idea is you're going to be given this list, and you just have to go through that list and say, of the factors that I currently of the spells that I currently have, and the factors of that number, of the index of that number, how many of them overlap, and does that cover this number right here? And if it doesn't cover that number, that means that that value, that ith value, is the index. So I had to write a function to get the factors. Again, I'm kind of a fan of doing the iterator thing after we did that the last time. So this, it may not totally be readable, but it is a way to get factors. And I looked it up from a previous problem that we've solved. I didn't know this off the top of my head, so I looked at a previous problem I'd solved that had factors in it. You know, you do a grep for factors, and then you find that code. And then I made it. It wasn't functional like this, but I like the idea of doing iterators. So I did an iterator, and then I made it functional. And what is it? Well, the way you determine a factor is you just say you go from 1 to the square root of that number of n, the number you're trying to factor. And then for each of those, you only track if it's a multiple of the number, right? Obviously it needs to be a multiple. And then you do a flat map y, because you're tracking, there's a potential for you to have 2 values, but you could also only have 1. And that has to do with like the perfect squares. So if you were just doing this algorithm, you'd wind up with like if you were doing 4, you would first do 1 and 4, and then you would do 2 and 2, and it would be 2 and 2. And you're like, oh, wait a minute, that I don't want to add 2 twice to this list, so I don't want to include that one. And so that's what this if block does. It basically says, check to make sure that I, or n divided by I, does not equal to I, meaning it's like a perfect square. And if it's not, then I add I and n divided by I. Otherwise, if it is a perfect square, I just add I only add it once. So this is going to have the effect of, we go through all the numbers from 1 to the square root of n, and we only filter by the ones that are multiples of the thing, right? Obviously, if you're looking for 4, 3 is not helpful. I mean, you wouldn't technically get to 3, but that's the gist of this part. And then we just have to say, okay, well, we know I is definitely on the list, but is it a perfect square? And if it's not, we also add n divided by I. And this is the reason you can do like the square root of the value, is because you're calculating these two at once, right? You're calculating 1 and 4, and there's no reason for you to like just do 1 and then do more work and do 4 later. You can do them both at the same time, again, as long as you're not a perfect square. Okay. And that's it. Well, that's it for calculating the factors. For part 2, what do you do? Well, now I need to I take my input and I zip it with my enumerate, but I'm starting at 1. So I do 1 dot zip with input. And now I can just fold this, right? Because I'm going to keep track of a hash set of my like uniquely seen numbers, if that makes sense. And this hash set, again, it's going to be the quote unquote spell. You'll see me use it later. But what do I do is I get the factors of that number, and I filter it by any of the values that I've already seen before, any of the spells I've already seen, and then I get that count. So that is these 2 parts right here, right? I'm going to get that count. And then I just ask myself, is that count less than my current value, right? So this is like the 2, for example, it's a 2, and if I only have 1 here, then I know I need to insert 2 as well. And then I just return that in my fold, and that gives me the thing. So what it wants you to do in this problem is, once you've figured out the spell, you multiply them all together to get the number. And so that's how you solve part 2. You just call the spell required on the input, you iterate over them, and calculate their product. So again, I hope that makes sense. We're just trying to get factors, and we want to filter by the factors that we've already seen, and that will give us a count of like how many have already contributed to a brick in that column. And then we can just say, if we're missing a brick, like we need another brick to like fulfill the count for this column, then we know that it's the current one. And so we just add that to the list, and we do that over and over again for all of the inputs, and eventually then we get all of the spells that we need to solve it. Hope that makes sense. This one, and you can see the part 2 is actually quite a large number because like your input is large, but again, it's kind of math heavy, but because you're like literally just iterating over the input, and this is like a, you know, a square root of n solution, it's relatively small, right? Like these you're only doing it for maybe 100, and each of the 100 you're only doing maybe like, I don't know, on average 5 or 6. So it solves really fast, right? Microsecond. I mean, the way that I think you would optimize this one as well as part 1 is you probably find some faster way to do these things that I'm doing, but you're essentially doing the same thing, I imagine. Again, I'm not the math pro, so maybe there's a better way to do that. But that's part 2. So what do we learn in part 3? Well, now they say do the same thing as part 2. I'm going to give you like a starting set or a starting brick layout, and I want you to calculate what the spell is, and then I want you to figure out how many columns you can make with this number. And it's some giant number. I have it down here somewhere. 100,000 million billion trillion 200 trillion bricks. You've got 200 trillion blocks or bricks, and you've got this sample column, and you've got your spells. So the question is like, how many of these columns can I like do over and over again? How many columns can I make from 202 trillion blocks? And that's a huge number, right? Absurdly huge. So I think what you have to be thinking about is when you're solving a problem like this is to say, okay, well, even if I iterate, even if my like loop is 01 or a trillion, that's not going to finish in any normal time. So you have to start asking yourself, how do I figure out how to solve this, right? And you can actually see, they say, hey, look, here's some examples. Like if you only want one block, given this input, you could only make a length of 1. And if you want, I don't know, whatever, 1 million, or if you have 1 million blocks, you can make this many. So this number is just huge. How do you solve huge problems like this? The thing that goes to my mind is like, obviously looking at the puzzle input, maybe there's a secret, but we've done a couple of these before, even in Everybody Codes. Like I think just the last couple days we did a cycle problem. And so like I was thinking cycles. And here's why it led me to cycles, that to maybe like give you some idea. The way to think about it, I think a little bit, is this pattern's going to kind of repeat. Maybe not this exact pattern, but a pattern will repeat. You will eventually find a cycle in this thing. And you can actually determine the cycle without even processing without even going through the blocks. You can do this mathematically. And the reason I say that is, you know what the cycle is given these numbers. If you're smart at math. And I am not smart at math, but I was smart enough to know, oh, well, how will this cycle repeat? It will repeat over the least common multiple of those values. And what do I mean by that? Look at these numbers here and ask yourself, when do they start over anew? Like, when would they start over anew? And the answer to that is when the least common multiple of all of these values happens, right? And so the disk one isn't one we've done before, right? But think about it. With ones, you're stepping 1 each time. With twos, you're stepping 2. With threes, you're stepping every 3, right? Like this. And with fives, and so they have these patterns, right? Let's just do these. And so the question is like, when will these all overlap? Did I not do? Oh, I did the twos wrong. Let me do this so it actually makes sense. Okay, and now I'm gonna draw it one more time just so you can see it, right? 1, 2, 3, 4, 5, 6. And then this is gonna be every other one. One, nope, not that one. And then this one's gonna be every third, right? One, nope, right? That two. Oh, it is 1, 2, 3. It's this one, and then it's this one. If it may be a little bit hard to see, but there's actually a pattern here. It repeats right here, right? Like this chunk is the same as this chunk right here. They're identical. Again, the numbers we were using were 1, 2, and 3. So how big is this one? 6, right? Well, that happens to be because the least common multiple, the LCM of this is 6. That is the number. That is the number that all of these are equally divisible by, or yeah, divide evenly by, without a remainder, right? And so if you were to add a number, you just kind of have to figure out what that number is. So if we add 5, so if we have 1, 2, 3, 5, now it's going to be some larger number, right? We know 2 and 5 are only ever going to happen with on the tens things. So we know the number is going to be like 10 or 20 or 30. And so the question is like, when does 3 happen, right? Well, it doesn't happen here. It doesn't happen here. It actually happens at 30. So we know that the pattern of this one is 30. So the LCM of this one is 30. And there's actually an algorithm to do this, which I'll show you in a second. But that's the general idea, right? Is like, you know that this cycle is going to repeat. It's going to start over when you've calculated the least common, right? And so that's the goal, is to find what this least common multiple is. You know this one is going to go 5, 10, 15, 20, 25, 30, right? And this one is going to do a whole bunch of them, and then eventually it will get to 30. And then this one's going to do a bunch and we'll get to 30. Obviously, this one, is basically anything 1 through 30. It hits, and so now 30 is it's the least common multiple of them all. I think that's the way, like, I learned it in high school, right? Is you kind of like fudge the numbers and figure it out. There is a way to calculate this though, and so it's right here in the competitive programming stuff. It says right here, the least common multiple is actually just the greatest common dividers by this formula, a times b over the greatest common divisor of ab. So now this is only for 2 numbers, so you actually have to do this iteratively. Right? So if you have these spells, you're going to say, well, what's the greatest common divisor? What's the least common multiple of these 2? And it will be 2. And then you'll do these 3, and it'll be 6. So now you do 5 and 6, and that gives you 30, right? And now you do 30 and 9, and you say to yourself, well, when does 30 and 9 overlap? 90 is probably 90, would be my guess, right? But that's essentially what you're doing, right? And so that's kind of how you figure out the LCM, is you do the GCD. So so here's the formula for LCM, right? A times b over the GCD of AB. Well, how do you figure out the greatest common divisor? Here it is right here. You're just like, for the 2 numbers, you keep dividing one by the other until there's no remainder, like you get to 0, and then that gives you your greatest common divisor, right? Kind of like track that number. So I'll show you what that looks like in code. Here it is. It's actually not that complicated, right? I actually took from a commenter of like doing this inline, right? Like, you can, instead of having a temporary variable, you can have like a left side and a right side as a tuple. And so I did that, right? So you just swap A and B, but before you do that, B becomes A mod B. And you just keep doing that. This is the remainder algorithm, right? Modulus. And you just keep doing that until B is empty, and now you have the greatest common divisor right here. And given that, you can calculate the least common multiple by using this. And again, I could probably explain these if someone's is like, hey, can you solve the greatest common divisor or whatever. It would take a long time to figure out and do it. I'm not super familiar with these. Again, I'm not super mathy. Even though I kind of knew this is how you would solve it, I didn't know it exactly. So I came here and grabbed these. Actually, I don't remember. I may have also gotten these. I'm sure we've used these before, right? So I may have gotten the num crate that gives you. I've used the num crate before. It gives you like some additional things like that are, useful. I think I've used that before in some places, and I think that also gives you these kind of things to solve. Anyway, that was a kind of a long-winded solution of like, how do you get this? But all that gets you is, so now you have you can use part 2 to figure out what the spell is. Now you can use the LCM of the sum of these numbers to figure out how big the cycle is. And we've done cycle detection before. So just again, like the generalized way, right, is you have some area, right, and you want to figure out where the cycle is. In this case, there is no prefix, so we don't have to worry about it, but you'll have some cycle and you'll say like, oh, this is the cycle, right? And once you know that's the cycle, you can just say like, how many cycles are there in this? So times, you times it by, the cycles left or whatever, like the cycles to get you here. So you just like copy and paste this over, and maybe it's like, oh, you can do this 10 times. So if you know the value of this one is, let's say this one is 100, now you know this whole thing is 1000, right? But you always have this like little remainder. And usually you kind of have to like kind of calculate this manually, right? You say, okay, well, I can get from here to all the way here, and this remainder part, maybe it's just like, maybe it's 47 is the answer or whatever, right? Is that little part that you have to like finish solving yourself. And so that's kind of where this comes from, right? Is the idea is find some cycle with this spell, and that will get you, of the 10 million or whatever, it will get you 9,760,000, and the rest of it you just got to calculate yourself. And I actually went to solve it that way. I just manually calculated it, and it was not solving fast. And the problem is for a number this large, even if you I guess I don't know what the actual thing is, but even if you only have like 5 or 6 numbers, it could be a large least common multiple. Like the least common multiple could be 10 billion or something like that, which means you're still going to have to there's some value of this that you're still going to have to calculate manually, right? And you don't want to calculate it manually, and that's where the bsearch comes in. So I'll show. But that's the general idea. Again, for this algorithm is, can let's figure out what our cycle is. And again, we can actually kind of figure out our cycle mathematically by discovering the least common multiple of our spell. So the first thing we need to do is figure out what our spell is, find the least common multiple of those numbers. That will tell us how big the cycle is. And now we can calculate what the cycle is and how many there are, and multiply that to get us everything we need, except for the remainder. Then we calculate the remainder and we solve it. So what does that look like? Well, we just call the spell required up here above, right? This is the function right here. I actually abstracted this to make it more easy. Part 2 and 3, it's essentially part 2, but you aren't taking the product of it. So I do the same thing to get the spell, right? That gives me the unique spells, that the same thing I did in part 2. That gives me the spells. And now I just need to get the least common multiple over all the values. And again, this was it happened to be a very functional day for me. But the way you do that is you just fold and you start at 1, and you do the least common multiple of all the values, starting at 1, right? So the least common multiple of 1 to 1 is 1, and then 1 to 3 is 3, 3, and then 3 to 5 is 30 or whatever, right? Like, is that actually, I think that is the least common multiple. I've said it like a few times and now I'm second guessing myself. But we can just fold all the values together and we'll get like the giant, and that will tell us like how long the cycle is. So now we just had to figure out how many blocks are in the cycle. That's actually not that hard either, right? Because now that we know how big the cycle is, we know how many blocks will be in there by how it divides by itself, right? So think about it. If the cycle is 100 and the numbers are like 5 and 20, let's say, well, we know we're going to lay a brick every 5 times or a block every 5 times in the 100. So it's just, 100 divided by 5 is 20, and then 100 divided by 20 is 5, right? So we know that the cycle length for 5 and 20 is 25. So we can just do that again with with a map, where we just say for each of the spells, how does it divide by that thing, right? And this is like integer division. So like 100 divided by 3 is going to be 33, right? Because it won't do it that last 34th time at all. And then we just sum those up. So now we know how big the cycle is and how many blocks are in there. That will tell us how many columns we can use now, right? Like how many columns. So we know we have this 202 trillion. And so the way that we calculate the columns is we say, well, take that total and divide it by the blocks times the cycle, right? So if we know we're going to create 100 blocks every and we're going to do that cycle 1,000 times, right? Then we know we're going to use that many blocks or whatever, right? And now we'll have some amount remaining that we just need to calculate, right? So the answer to the question is now, or the answer to part 3 is just, it's the columns, obviously. That's like the cycle part plus the remainder. And this is where I had to do a bsearch. Initially, I was just kind of calculating it manually by stepping through it, and it totally didn't work. It was not going to finish, and I suspect it was because like this remaining number, I didn't actually look. I guess we could do it right. That's not right. And that doesn't look right. Why is that? Did I do something wrong? I mean, I'm getting the right answer. Now I'm second guessing myself. Heck. Is all of this pointless? Wow. I did not realize that until just now. The cycle length is like larger than the number itself. That can't be right, is it? Holy cow. Is that really true? I Okay, so you really just have to do a B search of the values? That's absurd. That's crazy if that's actually the case. This whole what that's saying is this top of this code is like pointless. I did not even check this because I was just kind of doing math as I was doing along this. But oh, is that really right? What a trolley problem if that's the case. Oh, I still need to get no. I guess I still need to determine this. But what the? What the? That's actually hilarious. Okay, I'll leave my original solution in because it made me feel smart, but apparently it wasn't smart after all. You only have to do the B search. Okay, well, let's move on to the B search part and I'll explain it to you just so you understand. The idea is now apparently it's the whole puzzle, but it's this remainder part right here. So like if you think about this part expanding or this whole thing, let's try that, right? You know you have some number of at any point in time, the question is that you may be asking yourself is how many bricks will I have laid at this point? And maybe it's, 1500. And here, this one's always going to be smaller, right? So maybe this one's one, and maybe this one's, you know, whatever, 200,000. It's some number. You want to find a number that doesn't go over, we'll say it's 50,000 for this example. So what you want to do in this list right here is find the number that is the largest number that's less than 50,000. It's like the Price is Right thing, right? The greatest out. And this is actually and this is a B search solution. Often the B search solution is can you find the exact number, and that's when it terminates. But we want to find the greatest without going over. And why do we use a binary search? Well, let's talk about the algorithm first, maybe, and then it'll happen. Basically, what you do is you start with like you track three numbers. You have a low, a high, and then you have a mid. And the way it works is you start here and here, and then you put your midpoint right here, right? And you ask yourself, okay, well, what is the answer to right here? And let's say it's, I don't know, 25,000. Well, you now know that all the numbers below it are not going are bad. So they're no bueno. So you're never going to get the right number here because this one's like way too low. You know you could go higher. You do want to keep track of it, right? So you say, okay, well, I am going to track this as my like quote unquote best right now. This is the best I've seen so far. But now you can say, okay, well, I just want to do the same search, but now I want to do it from mid to high, right? So I can, and this is why it's called binary, is because we can cut this whole piece in half, and now we move the mid point. So we make this one our new low. So this one becomes our low. And our new midpoint is somewhere here in the middle, right? So this is no longer our low. And then we just ask the same question, right? So if like this one was 25,000, maybe this one is 100,000, right? Well, now we know that this one definitely can't be it, right? Because it's too high. So we know anything above that is going to be too high. So we just can't use this one at all. Sorry, I'm still reeling about the only thing you had to do was a binary search. That's totally hilarious. I did all that calculating for no reason. That's really funny. But anyway, we know that this part is not going to be part of it because you're at the 100,000 mark. But we know this one definitely is, right? And so we're going to say, okay, well, we'll make this one our new high, right? So this becomes our high. And now our new mid is going to be right here. And let's say it is, I don't know, 75. Well, we just keep doing this over and over again until we're going to eventually get a number here that's like 49,995 or whatever. Some number. You're going to keep doing this over and over again where you're going to like keep splitting it in half. And this is why it's called a binary search, because you're reducing it by half each time you test. And so there may say there's like 100,000 numbers you have to check. You now actually have to check the log n of that number, right? It's a substantially smaller number, maybe like 12 numbers you have to check as opposed to an infinite number. And it turns out you actually only have to, I didn't actually do any of this. That's fun. I still am mind blown by that. Because you didn't actually have to do any of this because you literally just binary search the whole state solution to find it. Because the cycle itself doesn't cycle over the life of this number, which is totally hilarious. But let's look at the binary search. This is just that same thing that I described in code. We were given our high, which was at the time our cycle, and we're just going to do a low. We're going to track our low and our best. This is the best one we've seen so far. And we do this while low is high, right? We're going to keep having it and having it and having it and having until now they're equal. It's usually when they become equal, but you do less than or equal. At least I always have, just in case. Eventually they will be equal. Yeah, I think this is the right way, right? Eventually, well, you want to do it one last time when they're equal, I guess is the way to say it, right? You always want to do it one last time. That's why you do less than or equal. So you just find the midpoint, which is the low plus the high minus the low divided by 2, right? So you find the midpoint of the two, and then you add, and then for this problem, we're saying, well, how many blocks is needed to go to that point? And well, we know, we just go through the spell list and we say for each of those, what is the mid divided by that spell? And that kind of like I was using up here, this gives us like the how many times that's divisible over and over, right? Or how many times it would be used, that spell would be used up to mid. So that will give us the number of blocks that we need at that position. And we just say, is that less than or equal to how many's left? And if it is, we found a new best, but we know we want to go to the higher end of it, right? So we move our low value to our mid plus 1. If it's too high, then we know we want to go smaller. So we now just set our high to mid minus 1. And we know it's too much, so we don't update our best. So the only time we update our best is if what we would need for that midpoint is less than or equal to the remaining. And that means we want to use this part. So this is, again, the effect is we're having the list that we're having the list that we're doing each time. And as long as that midpoint has a good value that we can use, we'll update our best. But otherwise, we're just doing the binary search. The way that you learn it in like computer science or a programming class is like you're given an array and it's a sorted array, and you can do a binary search to determine if a value is in that sorted array, right? And the way the algorithm is very similar. The only difference is you just check, is the midpoint the value? And if it is, then I found it. Otherwise, I check, is it less than what I'm looking for or greater? And that will differentiate whether you look down the left side or the right side of the middle point. And that's it. Okay, that's part 3 with a crazy gotcha. I'm still baffled. Holy cow. It didn't even occur to me to look that, I mean, what are the numbers? Is there just a whole bunch of them? Again, I didn't look too close at the puzzle input because I kind of had an idea of like, here's how I would need to solve it. It also explains why I tried to calculate the remaining manually and it just never finished, is because there literally was no remaining. I'm still blown away by this. So let's just print line the spells. I mean, there are some large numbers in there. Yeah, I could see why it would be large. Some of these are like very big numbers that, like 733 and 601, those are going to take forever. Like, I think the closer the numbers are to each other, like the more likely they are to like take a long time to catch up, because you basically have to like cycle through one like a bunch of times to get an overlap of the other. Okay, what a troll there at the end. I thought I was like, oh, look at this cool cycle management thing, when all you could really do is just do the bsearch of the whole thing. So that's hilarious. I got. But the cycle thing, I think that's kind of funny, because we had just, and maybe I was like, I misled myself, because I think we had just solved a problem where the solution was a cycle. And that's probably what led me astray. What a funny. Anyway, so I thought, oh, it's probably a cycle thing. Find the cycle. And I even did some math. I'm like, oh, I need to do the LCM. That's kind of pointless, because you don't actually need to do that. This one you do need to do, because you do the same thing down here, right? So you figure out how many blocks are used up to that midpoint. But okay, that was funny. I guess the only thing that really changes is you don't need like this stuff right here, right? And you just do a bsearch. But funny. Okay, let's see. We go look at my progress. How's my little duck doing? Oh, we're getting built. I don't know what the jargon is. These kids. What is that? Is that like? Do I now have armor? Oh, scales, right? I'm a dragon duck. Did mention scales. I now have some scales for me. Very cool. We only have 4 days left. That's crazy. We're almost done. Then I think I've mentioned this. Thursday is a holiday for me, so I probably won't be. I don't know when I'll actually be able to solve that day. I may be like hungover with turkey. I will have eaten too much turkey. It may make Friday a hard day to solve the problem. Do we see how everyone did? Again, I started like a little late on this day. That's actually not too bad. I think a lot of the days. Don't talk about day 10. Yeah, you can see I was about an hour and 40 minutes late, somewhere in that range, hour and a half. I still got points though, so maybe this was a little bit hard of a day. Maybe not everyone saw the trick or the trick. But yeah, 46 minutes. That's actually not too bad to solve it. Even knowing it was a cycle. I did, again, I copy and pasted even though apparently I didn't need it, the GCD and LCM. And I did copy and paste the factors, but I did rework it a little bit in that time to turn it into an iterator. I should say, like, again, I try and like redo my code after I've finished it to make it like much more readable. And so this spell required function wasn't there. It was a lot of copy and pasting here and here. And then these didn't quite look the same. I think I had this one. I think I did have like this. That one didn't change, but this one I think it was a for loop where I realized, oh, I can actually just fold. You'd be surprised how many times you can actually just turn a for loop into a fold, because you can track more than one value and stuff like that. It just depends on readability. Like, is this readable to you? I don't know. If you've had a lot of functional programming experience, then it might be. Otherwise, it may feel like magic. I guess that. Let's look at the leaderboard, see how everyone did. Only human. Okay, these are some really good times. I do watch Jonathan Paulson. I'll have to see how he solved his. I think I've seen a couple of his videos too, because he goes crazy fast. Let's just look at day 6. Right? Yeah, these are absurd. 4, 5, 7 minutes. I wonder if they figure these out via. They probably figured out the bsearch and didn't do the cycle. That's something I need to think about. Is like how easy, like the thing that makes you say, "Oh, do I even have to do the cycle figuring out?" Thinking about it in hindsight is how easy is it to calculate what I need? And that operation is just based on the number of spells in this case. So it's fairly constant, right? Like even if there's 100 of them, in my mind, 100 is essentially constant, right? And so doing a B search over this large number where you're only doing like quote unquote, 100 operations feels very small. And so I probably just said, oh, I can just B search the entire solution space for that problem. So that'll be something for me to keep in mind. I imagine that's how these are. You can go to these links and check them out. Okay, should we see what everyone did on Reddit? Is it absurdly easy? Did I get trolled? Am I the only one that got trolled? For blocks is the thing. Okay, here's another binary search, but again, I did mine iteratively. I tracked the min and max walls, count the blocks that would be used, and then this one's recursive. That's another way to do a binary search is recursive, right? So you update your min and maxes, and then you solve it that way. Very good. Is the sum of the wall divided by the value for value in pattern. Yep, this is the same thing. It's just this is the Python way of doing it. So, I mean, I do feel like I was doing it right. I just tried to do it with a cycle, and there was none found. I was up at midnight. Figured I'd give it a try. P1 was easy. I actually think in this one, P2 was probably the harder one to solve, even though I did P3 kind of wrong, which is hilarious. P3 was the hardest because it took me a while to kind of like figure out the factors. Does that bear true in my timing? It felt harder, but it wasn't. So the first part I did in 9 minutes. It took about 20, and then another 20. So they were roughly even in solution time. Okay. LCM. Okay, I use that part. Interesting. Like it's pretty fast. Part 3 was interesting. Oh, do I overflow? That's interesting. I may overflow. So you just do a search. Okay, so that's a fair point. Is I may actually overflow here. Kind of want. Well, there is actually no remaining, right? Okay, I'll get rid of this stuff because I actually think that solution makes a fair point. Is that there's it if it overflows, it may actually lead you. I didn't look at the LCM. If it overflows, it may actually get you the wrong answer because you may think you found a cycle when you actually haven't. I think I just lucked into that because my number was larger but didn't overflow. So I'll keep this as is. But that was actually kind of trolly. Some simple math, but really large numbers. I actually had this problem too. My test cased work, but my input didn't, and it probably was the difference between int and big int. So spell power. Okay, so this is calculating. I think I did that with an iterator, right? It's like for each spell, it's the value divided by. Um, yeah, you do that over 90. Find spell. This is an interesting way to like. It is kind of doing factors, but the what it's doing is like for each of the numbers, as long as it's not 0, you like add the number plus 1, and that becomes your k value, and then you're tracking those things. Okay. But you just do the product inverse spell. Versus part 1. Okay, that is correct. Oh, that is an interesting way to figure it out, right? Like I think it comes out to be the same way. This is just a much more mathy way of doing it. The way I did it. Like I did it with an iterator, right? How is this jumping? Oh, you have some large number that's the inverse spell, and then you step by like 4 loop. Very interesting solution. This is much mathy, I think. So okay. Binary search. Okay. I definitely got the binary search. It was just way over the. Oh, this is another way to do the div ceiling. Like in my code, to get over the division thing is like high minus low, low plus high minus low divided by 2. And that like gets you the. I guess that gets you the range, right? Am I even doing that? I. Oh, it is, right? Because this gives you like how far you are away from the low. Yeah. So, because the low is going to be some, like say it's 10 and the high is 20. You want to do 10 plus another 10. So 20 minus 10 is 10. 10 plus 10 is 20. 20 divided by 2. So point low plus 10. I probably didn't say that right now that I think about it, but I did have it right. This is another intro. Actually, why does this one lower plus? Oh, that yeah, that works. Okay. They both same spell or map. Okay, yes, I did the same thing here. And you basically okay, and you just say, is it greater than the number of blocks? If it is, I guess the thing to note about part 3 that I didn't, my solution could be simplified a little bit, is like I'm tracking the best in here and going through it. But actually, so how does this, that must suggest that there's an exact number to get you to that thing, right? Or am I wrong? Is it that this low will always be, you make the low the mid plus 1? No, I don't think that's the case. At least the way that I implemented it, it's not going to be the plus 1, right? So they always made the low the middle, and then they stopped there. And so that would be the case. That's why it works, is they kept the low the middle. Usually, at least the way that I've always done it before, is like you move it up 1 bit. So yeah, that works too. They're both doing the same thing. Mine's just doing it differently than theirs. So it all works out the same. Off by 1. Okay, mine does not have the off by 1 issue, and that's the issue, right? So I'm doing this, right? No, I'm doing this one. Right? This is the way I've learned it. Okay, so this is the thing that I was missing, right? Is they're saying, oh, look, if you actually do the ceiling of that value, then the middle value is the value, which becomes the low. And so eventually you get there and it becomes, okay, that's a cool thing I didn't know about a binary cert. Very cool. I'll have to remember that the next time I am. Or should I just try it right now? What am I going to do with the rest of my. Okay, so it would be. I actually think this is still the same, but it's the seal. But I don't need to track the best because it's gonna. Mid. Oh. Okay. I don't think it changes the algorithm much other than you're not keeping track of the secondary variable. But yeah. Okay. I think that is a cool optimization, is like you're technically using one less variable. Kind of cool. Mhm. Let's see here. Python. Description for use me. I work with answer. Reconstruction of the pattern. We have talked about, well, I don't know that I have, but the sieve of Erast. Okay. Yeah, it looks like most people were smart enough not to try and figure out the cycle. That's fun. See some C. Yep, there you go. Not too hard. You do. This is a thing to keep in trying. Sometimes it's okay to, like what I've done before, especially when I'm doing modular arithmetic, is like shift the one base to zero base, and then it works. It kind of works out the same as the end. You just have to decide how many times you're going to do -1 versus make it less or more readable. Number of columns. Take the values. Okay. Yeah, these are, so this is like a one line for loop of doing the same thing, right? Is these are going to get your factors, and then you're going through those and seeing, do I need that? Yeah, okay. They did the same thing as me, and then they realized, oh, I can just do a bsearch. Yep. Okay, that's hilarious. I'm glad that means at least there's one other person that did cycle detection, and then I honestly would not have known if I'm like, oh, maybe I should show what the remainder is, and then the remainder was the actual number. Yeah, I don't think there is a math way to do part 3. I think you just do a bsearch over the space. Or again, I'm not the math smart person, so. Well, this is a fun rusty way to do the result. So I think because I learned all this stuff in like C, it's in my mind to do this if block, but you could also do that, because if it is when you're actually doing a binary search, not in this case we're looking for like the best value, so that's not always going to find the value, right? If that makes sense. But if you are doing a binary search, normally you'd say, oh, if I've ever found it, now I know where it's at, what position it's at. And you might just return true or whatever as opposed to false. So using a match operation like this is actually kind of a cool way to do it. Uh, more more rusty way of doing binary search. Wait, what was that? Oh, this isn't the same solution. Oh, you can kind of, so what they're doing is they're saying, oh, maybe I don't start exactly at this number. Maybe I start at some like higher number, and that reduces my space for the binary search. I don't think that's necessary. Again, the cool thing about a binary search is it like literally splits it in half, right? So like just to illustrate that again really quickly. You start like with some huge space that's ginormous, and you split it in half, and then you split it in half, then you split it in half, you split it in half, split it in half, split it in half, and eventually you get to the number right here. And think about it, you've only done 1, 2, 3, 4, 5, 6 operations, but that could have been over, 1 billion. This was another one, the binary search thing. If you've just done programming your whole life and haven't really like taken a computer science class, that's totally okay, right? I know a lot of programmers that haven't done it, but they were doing a thing, and I was like, oh, you know what, that you could actually just do a binary search, and they're like, I don't even know what that is, and so I showed it to them, and like it boggled their mind, right? The idea is like, oh, I can do this over a space of 6 or whatever. It only takes me 6 operations to find the answer, as opposed to like their solution was taking 1,000. Very cool thing to learn and to keep in mind. 1670 cries. Yeah, it is annoying when you think you know, when you're actually doing well on the leaderboard, and then it's not. Doesn't have to. Split, map number, map math. Yeah. Okay. Yeah, very cool. Yeah. This is like a slower-ish way of doing factors, but still works totally fine. Yeah. For mapping values, known answers. They do up the factors. Okay. I don't know if you need to like do this because of the way the binary search works, but this solution looks similar. It's just JavaScript. The previous one, that dialogue APL. I don't even know how to put these on my keyboard. I would have to like Google each of these things. Okay. Okay, I think that's enough for now. This was a lot of fun. I had a lot of fun doing this day. Got a little trolled at the end there in part 3. Thought I was being smart. I mean, I did get the binary search part, but the cycle detection thing, totally pointless. And there you go. What do? Some days you do more work than you need to. But I think all in all, it was still a fun day. Doing these like again, we've seen these brick style laying things before, and because of the variations and the questions they ask about it, right? It's always just I think it's probably good regardless of whether I use it. The factors thing is helpful, so always knowing, can I get some factors and what do those factors look like, and then least common multiple, greatest common divisor. Those are pretty common. Even if you don't know how to implement them, like I didn't, I had to copy paste. Um, the ability to say, oh, this is a least common multiple problem, or this is a factorization problem. Those type of things will go a long way. So with that being said, I've had a lot of fun, everybody, and we'll talk to you next time. Bye.